Thank you everyone for coming. It's a privilege to be here today with my colleagues Ken.
Hello.
And James.
It's nice to see you all here this morning.
My name is Jordi Mola. I'm the architect and engineering lead for these time travel debugging tools, and we are happy to present them to you today. So I got the clue from a great presenter one time to start with questions up front. So I'm going to open Notepad and type a few questions from the audience. If there is any question before we start, just go ahead.
I want to know how this differs from RR. I mean, aside from the fact that the platforms are mutually exclusive.
How does this differ from RR? Okay, there was another question here up front. Sorry.
Like Windows only or like?
Okay. Windows only.
And which Windows?
Oh, which versions of Windows? Okay, let's just start with those, and then I'm sure that there will be more questions as we go forward. So, what is time travel debugging? Okay, time travel debugging, TTD, not test-driven development, just time travel debugging, for short TTD, is a reverse debugging solution. So we record the execution of the process. Think of it as a movie. We take a movie of the process execution. And as a movie, when you have a DVR or a DVD or some of those things, you can go forwards and backwards to look for things, but also you can search through the traces using queries. Ken will do a demo on how to do queries to search through the trace. When we look at debugging, we set up to solve a few problems. Debugging is time-consuming. I'm sure all of us here have a single step through a function painfully to make sure we didn't get past the point of the function that was of interest and spend an hour just single stepping to not yet be at the point we wanted. Debugging is really hard. We actually will do a demo today of debugging a garbage collection bug that can be very nasty to debug without some of these tools. Debugging is complex, so we made sure that we didn't have to learn new things. All of the things that you are used when you debug live, breakpoints, single stepping, going, memory breakpoints, work on backwards debugging. And finally, this is a pet peeve of mine, the number of many times you have to repro a bug when you're debugging normally. You have to go and, oh, I learned something, I start over. Because it was a little bit earlier than I thought. Now I learned something else, I start over, and in time travel debugging, you just simply have to go back. Some of us have used the trick of binary searching a bug. Just look for a place, is the bug happening? Not yet, okay, it's in the second half of the trace, and move on. A little bit of background and key features for this. This is based on a Microsoft research project that was internally available about 10 years ago. But 3-4 years ago, we decided to make this publicly available. So we went and did work to convert the research code into production code. That was an effort. We also feel that we are ready for preview, but it's a preview, it's not final. We still have some bugs and several areas to work on. In particular, for those that have worked at Microsoft and have used the research technology, our replay is about 2 orders of magnitude faster than it was for the old tool. Record is still as much overhead as it was before. Is something we will be working on the upcoming months and years. It's written in C++, but it's C++ of different kinds. The recorder is a piece of code that we inject inside of the process that we are recording, so that uses no exceptions, cannot allocate memory. It has a bunch of restrictions that resemble embedded systems. On the other hand, the replay code is normal modern C++. It uses coroutines, vectors, maps, the parallel library. I mean, it's a normal C++ piece of code, performance sensitive, but normal. Okay, our recorder is multi-core. That's one of the differences with the RR project, since it was one of the questions. We do not single core the execution of the process to actually record it. If you have 50 runnable threads and 50 cores, we will use all 50 cores. This is important for us at Microsoft because this is used on things like change servers that run on 64 core machines, 128 core machines. So it was an important aspect for us to make sure that we could use a significant amount of that machine when we were recording. And this is used a lot in escalation cases. When you get to escalation engineers at Microsoft that are working with you and your company or you in your consumer side, and you get to people that have to debug your machine, this tool is used often. I have been quoting numbers above the 50% of the cases. The tool supports shared memory and asynchronous I/O, another different with the RR project. And we have the ability to query the trace. And again, Ken will do a demo of that, which we think it's an interesting approach to debugging. If you take one thing out of this here is this tool runs in 3 steps. You record the execution, you index the execution, the debugger does it automatically for you when you open the trace for the first time, and then you replay, you consume the trace in the debugger. We have done a few blog posts. We will do more. There is a bunch of documents. There is how to download this. You have here a link to go and play with it. How we use this at Microsoft? How do you use time travel debugging at Microsoft? We use it to resolve problems from customers, and we use it to resolve problems internally. There are teams at Microsoft in Windows, which is the organization we are in, that will not ask you for a repro of a bug. They will ask you for a trace of a bug. A trace is essentially one of our recordings. So you don't give them, do these 15 steps to repro, and then you get back it doesn't repro my box, which we all have used as an excuse at one time or 2 or 3 or a few times. You get the trace to them, and that also bugs that have traces on them have a much higher chance of getting fixed than bugs that don't have traces with them. This is awesome for bugs that are difficult to repro. If you have captured the repro on a trace, you have it, you don't need anything else. Corrupted memory, we will see that on an example. Race conditions, resource leaks, it works very well at this type of problems. How to get it? It's part of the WinDBG preview toolset. And here you have a link on the post that has how to install it, a video of how to use it, channel 9. There's a sticker on one of the sides of the laptop for that. But instead of explaining a lot of what it is and how to do it, let's go for demos. James?
Thank you, Jordi. So yes, some things are much easier to show than to talk about. So I'm going to walk through 2 demos of using time travel debugging. In the first example, I'm going to show how you can record execution of a process and then take the trace that is produced and actually debug it in the debugger. So the first thing that you're going to need to do is open WinDBG as an administrator. So you have to have it open as an administrator in order to record a process. If you've never used WinDBG before, this is it. If you have used WinDBG before, this may look a little different than what you're used to. So this is a few weeks ago, we released the first preview of this new WinDBG UI. So we're trying to make some major user interface improvements. It should hopefully be a lot easier to use. But it uses the same debugger engine under the hood. So if you're familiar with a bunch of WinDBG commands, all of that works just as well as it did in the old one. We're really happy that we've made some big steps forward with WinDBG here. And now that we're adding reverse debugging, we're looking forward to making a lot of steps backward as well. So what I'm going to do is I'm going to go to the File menu, and we have 2 options here that support time travel debugging. So we can either launch a new program, or we can attach to a running program. So I want to run my own little test program, so I'm going to pick Launch Executable, and I'm going to type in the name of my program, which I've conveniently named test.exe, and then I'm going to check this record process with time travel debugging. Now, when I click OK, what's going to happen is the debugger will run this program, and it will be recording everything that it does. The debugger won't be attached to the program. It's just going to be letting it run normally with the recording active. So I'll click OK. And we'll see the program start up, and it's just a little test program. So it prints out some strings and then returns. I'm going to open the source file so we can take a look at it. And so we can see here just this very simple program. In our main function, we have a vector of strings. We iterate over the first 10 letters of the alphabet. We create a string for each letter. We print it so we have something interesting to look at while we're running the program. We add the string to the vector, and then we sleep for a little while so that the program actually takes a little time to run and it doesn't exit immediately. The first thing to note is that when you open a trace, it starts off at the very beginning of where you started recording. So here we can see we're very early in the execution of the process. Now I want to get us into the main function, so I'm going to add a breakpoint at the end of the loop, and I'm just going to click Go. And so what the debugger has now done is it's replayed execution of the program to the first point that it hits that breakpoint. So we can see in the stack window, we're inside of the main function, which is where the breakpoint is. And we can see in the locals window, we can actually see all of the local variables, just like we would if we were debugging a live program. So we can see the current character is A, we're in the first iteration of this loop, and there's one string inside of the vector. So if we go, a couple more times, we can see it advances through the program and it just keeps hitting that debug or that breakpoint over and over again. So there's a few things to point out here. The first is that so all of the visualizations, so for example, WinDBG uses the same NatVis visualizers that Visual Studio does, so you get all of the rich ability to inspect STL containers here. I mean, this is a vector of strings. Looking at that just in raw memory can be rather tedious and painful. The other thing is that all of the debugger commands you're used to with live process generally work. So for example, we have a G command to go forward one step, or one that will run the program, and you can see that we've advanced again to the next time that that breakpoint is hit. In general, most of the commands you're used to using will work. The one set of things you can't do is you can't do anything that would change the state of the program, because again, the program's not executing right now. We're just replaying what already happened. Finally, I wanted to note here that you'll notice that you don't actually see the console window. So when we ran the program originally, you could see the console window printing out the text. The reason for that is when we replay the program, or when we replay the trace, everything is contained within the debugger, so we don't actually do any of the side effects that the program had. So for example, if it did any I.O. on the disk or on the network, we're not going to actually go back and try and read those files or do that network I.O. again, which is very important. Additionally, if while you were running your program and tracing it, your computer lit on fire, and you somehow salvage the trace, don't worry, if you run it in the debugger, your computer isn't going to catch on fire a second time. So all of that is well and good, but this is a reverse debugger, so we also want to be able to, well, reverse execution. So you can see here on the ribbon we have the normal flow control buttons to go and step into, and we also have, for time travel debugging traces, reverse flow control buttons, so we can go back or step into back. So if I click the go back, what it will do is it will be as if it replays the program backwards, and it'll stop wherever the previous stop was. So in this case, it'll stop the previous time that this breakpoint was hit. So if I click that, you'll see we're still at the breakpoint. We've just hit it the previous time that it was hit. So in the locals window, you can see instead of the current letter being D, it's now C. There's only 3 elements in the vector, whereas there were 4 before. So we had a G command in the command window that would let the program go forward. There's an equivalent G minus that goes backwards. So if I run that, we're now again in the previous iteration of the loop. If you're familiar with using the P and T commands for stepping, there's also P minus and T minus commands for stepping in reverse. So those are the basics of how time travel debugging works in the debugger. But it's a lot more interesting if we look at how to actually debug a real bug. So to that end, I thought since we were the first breakout session, I would welcome you all to the conference. So I wrote a little program to print out a greeting for you. So we can see here it says, "Hello everyone and welcome to CppCon 2017. Enjoy the conference." So consider yourself welcomed. Oh, it also seems to have crashed. That's kind of unfortunate. So thankfully, I have a crash dump for this that we can take a look at. So I'm going to open up that crash dump and we'll see if we can figure out what went wrong. So I'll open the crash dump that we had for that. And I'll look at the stack window, because hopefully it'll show us where the problem occurred. And I see we're inside of a bunch of exception handling, and then I see here, that doesn't look like any of our code. And nope, can't, So there's not a lot of information here. So I saw this bug happen this morning, so I also recorded a trace. So I'm going to go and open the trace and see if we can debug it a little easier. So this is the trace I recorded earlier. You can open it. There's that open trace option on the file menu. And again, when we open the trace, it starts off at the beginning of the trace. So one thing that you can do, if you want to move to another location, we have a bang TT command. So I can run bang TT, and one option is you can pass it a percentage. So I'm going to pass 100%, which will move it to the end of the program. And what I wanted to point out here is this shows you we're in almost we're basically the same place we were in the crash dump. So again, the program was crashing, so this is where we would expect the end of the trace to be as well. And I can move back to the beginning using bang TT with 0 to go back to 0%. So since the program crashed, I'm going to assume that it's because an exception occurred and the exception was not handled in the program. I don't know if it was a C++ exception or something else, but chances are it was an exception. And so I want to find where during execution of the program that exception occurred. And to do that, I'm going to use a feature of the debugger, a relatively new feature called the debugger data model. So the data model provides a uniform and simple way to get all sorts of information about the thing that you're debugging, in this case, the trace. So I'm going to use the dx command, which is used to query the data model, and I'm going to look at the current process, which is kind of one of the root-ish things that you can look at. So in here, we can see the name of the program while we were tracing it is greeting.exe. That was the name of my test program. We can see the process ID that it had while it was running. And then we can see a bunch of other information that we can expand. Now, the information we're looking for is time travel debugging specific, so I'm going to expand this TTD node here. And then we're looking for an exception event, so I'm going to expand the events list. So the events list will have an event in it for every time that a DLL is loaded or unloaded in the process. It'll have an event for any time a thread was created or terminated, and then it'll have an event for every exception that was raised. So if we see here, there's one exception in the list, so that's probably what we're looking for. So I'm going to click that entry, and then click exception to see the exception-specific properties of it. So we can see here it was a hardware exception, so it was something that was actually raised by the CPU. It wasn't a C++ exception or some other kind of software exception. We can see the program counter where the exception occurred. We can see the exception code, so in this case I know this is the exception code for an access violation, so it's likely that our program either tried to read, write, or execute some memory we didn't have proper access to. But most importantly, it also has this position field, which tells us the exact location during execution of the program where the exception occurred. So what I can do is I can click this time travel link, which will actually take us directly to that point. So that's moved to the debugger, so we're now looking at the exact point where the exception was raised during execution of the program. Now we can see here in the stack window, unfortunately it still doesn't tell us where it happened. We can see that instruction pointer, which was the instruction pointer where the exception occurred, but the debugger hasn't been able to decode it. It hasn't been able to tell us like what function it was in, or even just what DLL that was in. So that's not particularly useful. Additionally, I noticed that the stack pointer here and the base pointer are pointing to two completely different locations in memory. So between these two things, I'm kind of guessing this was a stack corruption. So someone overran a buffer on the stack or otherwise corrupted something on the stack, and then when they returned from the function, that ended up corrupting the CPU state with an invalid instruction pointer and base address. So, you know, from our crash dump, we wouldn't have even gotten to this point. Like, it would have been very difficult for us to figure out what was going on here. Now, if we had a live repro, it might be inconsistent. It could be very difficult to figure out from that. But we don't have either of those. We have a trace. We know exactly what the program did, and so we can just walk backwards and see what happened. So in this case, I want to get back to before the CPU state was corrupted. So before that return statement, loaded that invalid instruction pointer, so that we can look at kind of get an idea of where the exception happened. Now, I think that happened recently, so I'm just going to step back a few times until we get a reasonable looking context. So I'll step back once, and that didn't change, so I'm going to step back a second time. And you can see now we've stepped backwards. The next instruction that the debugger would execute is a return instruction, so we've stepped back to before the return. And so we see now that the instruction pointer, the debugger now knows where we are. We're inside of the main function. The base pointer is still incorrect, though, because we haven't stepped back to before that was corrupted. So I'm just going to step back once more. And now we can see most of the stack, and we can see we're on the last line of the main function. Now, we still can't see our caller, and the reason for that is that we've stepped back to before the CPU state was corrupted, but we still haven't found where the stack itself was corrupted, so the return address is still incorrect. Now, I'm just curious, so now that we have our base pointer, I'm curious what's there on the stack. Now, we'd expect there to be two pointers there. We'd expect the instruction pointer to be there, and we'd expect the previous frame's base pointer. So I'm going to open up the memory window and just copy that address in and take a look at what's there. That does not look like pointers. That looks like the end of the string I printed out earlier. And if we scroll up a little bit, we can see, yes, there's the rest of the string, so definitely we've corrupted the stack somewhere. So the trick now is to figure out where did that happen. And so what I'm going to do is I'm going to use a breakpoint and then run the program backwards and have that breakpoint stop on the exact point where we corrupted the stack. So to do that, I'm going to use this BA command, which is break on access. I'm interested only in writes to the 4-byte location. starting at that base address. So basically, whoever writes to that pointer, this will stop. And at that point, all I have to do is click go back, and we've now stopped at the exact instruction that corrupted that pointer. And we can see, so it's inside of the string copy function, which is expected. We were copying, some string into this buffer on the stack. I expect the bug isn't in the string copy function. I used to work on the C runtime, and I'm pretty sure we didn't have bugs in that particular C runtime function. So I'm going to look in this get CppCon greeting function, which is the first function in our program on the stack. So we can see in here, this function just takes a wide character buffer and the size of the buffer. It has the welcome message, and then it copies that message into the buffer. We can see in the locals window, we can see the message points to the complete message. We can see that the buffer has only part of the message, and the reason is that we've stopped partway through the copying of the message into the buffer. And then we can see that the size of the buffer is allegedly 100 characters, or hex 64. So I'm going to guess that that's not correct, given that we've overrun the actual buffer. So I'm going to look at our caller and see what it passed in. So we can see here, the buffer actually only has 50 characters. Well, there's our problem. And the problem is, well, I accidentally passed size of greeting instead of greeting.size, so I passed the number of bytes instead of the number of characters. So, whoops, I'm going to blame my code reviewers. But actually here, so with this little test program, it's only 20 lines of code. Like, we could easily have gone and just looked at the code and diagnosed this and figure out what was going on. But in a large program, debugging this kind of thing, especially if it's a hard to repro bug, or if it only occurs occasionally, or if you're just getting crash dumps from the field, this can be extremely tedious and difficult to debug. So time travel debugging, works just as well with large programs as it does with small ones. And Jordy will be showing an example in a minute of debugging a large program. So in our first demo, I showed you how you can actually record a process using the debugger. I showed how you can step forward and backward, that you can use all the same commands you're used to using with debugging live processes, with the exception of things that modify the state of the program. In the second example, I showed you this debugger data model that provides you a very rich way of querying information about the process, and you'll see more of that later in our upcoming demos. I showed you how you can find events easily, so we were very quickly able to find the exception and navigate right to that point during the execution of the program. And then I finally showed how you can use memory breakpoints to quickly find who last modified something, which is often the thing that we do most with these traces, right? Like, you see some data and you say, how did that get there? Well, this makes it very easy to go and find that, right? You don't have to go hunting around and see all the places that might write and try and divine where they came from. You can actually go directly to the location where that write happened and find it directly. So with that, Jordy is going to show a much more, I guess, large example.
Thank you, James. So we wanted to show you an example with production code that is used normally. So we picked the Chakra engine. This is the JavaScript engine that is used in Edge and in IE. And I need an excuse to put the console debugger here since I'm a console debugger user. So we are going to demo the Chakra engine inside of the debugger. The debugger is scriptable in JavaScript. And we are going to just look at a bug in Chakra that way. So what we did was inject a bug in the Chakra engine that is not that different from the bugs that happen normally in production, except it has a nice comment next to it. When we find it, it will be obvious that we are there. Wrong click. So with that, I'm going to launch the debugger, conveniently in the debuggers folder. And I'm going to run this live first. So when the debugger comes up, I'm going to this is the console debugger. It's the same debugger we were using in the console. And I'm going to load the JavaScript engine that has the bug injected in it. So let me put the backslash here just in case. It loads it. And then I'm going to run a JavaScript script that all it does is allocate some memory, use some memory, and force some garbage collection. So it just puts some pressure on the garbage collector. It really doesn't do much more than that. And okay, it has loaded the script and it has executed it. Second time, okay. This third time, it crashed, and if we looked at it, it's an access violation. We see here that it's trying to read from this awful memory location here, which is -2, probably not the right address. And we see in a stack that is quite intimidating. In fact, okay, this is memory recycler, realloc. If I have to figure out where I got this -2 from this color stack, is going to be painful. In particular, garbage collection bugs have the root cause usually at the distance from the side effect. In fact, if you took a dump from this and looked for this -2 pattern, you will actually not find it that much into the trace, into the dump. It's not there. So that makes things a little bit harder. Let's repeat this case now with recording a trace. So what I'm going to do is do the same thing. I'm just going to record it. And when I launch it, what you will see is that there's some overhead with the record. In fact, the debugger has not yet come up. If I have time at the end, I will show you a case where things are a lot of overhead. Still usable, but a lot of overhead. Let me do the same things as before. JS provider.dll, load the guy that has the bug. Let's run the script that we were running before. And you can see it's a little bit slower. And despite this, as I said, this is used on more than half the support cases from escalation engineers. And that was before the performance improvements that we did in the consumption side. Okay, so it crashed like the other one. It's indexing. So for expediency, I'm going to debug the same thing that I have recorded on an unoptimized trace. There is an upcoming Channel 9 video, I think comes out next week. It's in post-production, where we debug this both optimized and unoptimized, so you can see that it works on both cases. This is a trace of the recording unoptimized, so it makes more C++ debugging. And James already showed us that we can look at events to find the exception. So I'm going to do it differently, which is just tell the debugger to go, and it will stop at the exception. Is, you know, first chance exception, this exception may be handled. Okay. To show to you guys a little bit how this also works the other direction, and is let me go to the end of the trace and go backwards, G minus, and we are stopped on the same spot. So that's a little bit of how it works forwards and backwards. Everything works normally. As before, we have this wonderful -2 here. In fact, it's the this pointer here, -2. Let's go back a little bit and see if I can figure out where this value comes from. So T minus to go back, or if you prefer, press the button in the UI. Now here we have this, the C++ expression, memblock. Ooh, memblock is also -2. So that dx command that James was talking to us about can be used to also look at the local variables, memblock. And it has a C++ syntax parser. So the ampersand sign in C++ gives us the address. The ampersand sign will give us the address. So this is the address of that -2 value. So I'm going to do the same thing that James was doing. Put a breakpoint, 8 bytes, BA, when someone writes these 8 bytes on this address. And I'm going to ask the debugger to go backwards. What this does is it stops at the spot where we wrote the value. Now, memory breakpoints, when you're debugging on a processor, a stop at the instruction after the action took place is the same here. So this is the instruction after the write happened. If I do one step backwards, now we are at the instruction where this thing happened, which is memblock will get the value assigned. And in fact, you see memblock has the previous value still here. I don't see free object list, so let me explain this pointer. Oh, is it this pointer member? So fine. dx free object list, this would work, or dx this free object list, the same thing. And as before, an ampersand will get me the address. So now I can do the same thing as before, put a breakpoint on this address that I have here, and ask the debugger to go backwards. Now, a couple of observations. The address I just was looking at, this first address, is no longer of interest to me. This is the value that now has the previous value. It's no longer the -2, so I'm going to disable this. And the other thing is the debugger, when it's running live, has a limit of how many hardware breakpoints, how many access breakpoints you can put. In Intel processors tends to be 4. Now the processors may be different. With debugging a trace, you have no limit. You can put 100 of these breakpoints and it will just work. So that's another advantage of debugging a trace and another reason why it's used often inside of the Microsoft. As before, we stopped. Now I stop on the instruction after, so let me go one step backwards. And I see this here. I look at memblock. It has an address. I see free object list. And okay, it has the new value, the old value, not the new value. Let me stack into the function. This is the same function as before. Let me look at the values here. It's -1, not -2. But if I look at this piece of code here, in fact, if we go back, we can see it. That's how the -2 came to be. Okay, so now the question is who put this -1 here. Let me copy this address. Let me step backwards. Let me put a breakpoint and type correctly the term. Let me list the breakpoints. Let me remove the last one I checked because it's no longer of interest and go backwards. And now here I see the value -1, which looks promising. And I see this demo introduce a bug. So that's the bug that we're looking for. And to be clear, I am not familiar with this code base. I have only used it to prepare for this demo. The person that did the JavaScript integration on the debugger in our team is not me, someone else. And we made something that was hard and difficult, quite easy to do. It was mechanical. I just followed a recipe. And it's not always that easy, but it often is this easy to debug bugs this way. Excuse me. Now, if we had to do this normally, for those that have enough memory, this stack looks nothing like the stack that we had on the crash. In fact, this crash happens over 100 million instructions before the root cause. So this is not going to be something that you can do manually by hand the old-fashioned way. So let me stop debugging. Let me go back to the slides. Let's take a look. What we have seen is that there is overhead when we record. You get a lot of value out of it, but there is some price to pay. As I said, inside of Microsoft, we use this a lot, so we find the price reasonable, and it's something we will be working on. If we have time at the end, I will show a scenario where it's much more clear that there is overhead. Hard problems become easy. As I said, I have not seen this code base before. I just followed a mechanical recipe of just follow the breadcrumbs backwards till you find the place where it does not look like the right thing to do. And the other thing is I had one trace to do this. I did not have to restart the debugger over and over every time I learned something where this came from. Oh, since it's backwards, let's go and find it. And so with that, Ken?
Thanks, Jordi. That was pretty awesome. Like that. Okay, so what we've seen so far is a pretty familiar debugging experience. Setting breakpoints, looking at the stack, executing forwards, now executing backwards. But time travel debugging allows us to look at code execution another way. It lets us look at it as a queryable data source. So what do I mean by that? Imagine you had a SQL database table where each row was a point in time in your execution, and that there was a set of columns that represented the register state of your processor and the contents of your address space. That would be a really big table, but you could imagine doing queries that would find specific call patterns, memory access patterns, things like that. What we have done is we have enabled this kind of querying in time travel debugging. Another kind of way to think about it is if you've used the sysinternals tool process monitor, right? You have a workflow of capturing activity in a file, then you go to the filter and you narrow it down to your specific problem that you're interested in. And we are trying to bring that kind of power to debugging your programs. So to illustrate that, we took a Windows SDK sample for a media player and we introduced a bug into it. And so let's see what that looks like. Okay, so imagine it's 4 p.m. on a Friday, you're getting ready to go home, and you get an email like this one. I was trying to use your program, and this is what I get. And we see we have the dubious error message, the operation completed successfully. So how many people have seen this one in the wild? Excellent, excellent. So, all right, well, let's see if we can use time travel debugging to solve this quickly so we can get out of the office. So we are going to go here. So, I could have asked Jordy for repro steps. Maybe he didn't remember what he did exactly. Or I could sit in his office and have him hover over me while I try to debug it, which is kind of intimidating. So I just asked him, please send me a trace file. And so he sent me a trace file. And so let's open it up and see what it looks like. And let's stop debugging just to make sure. And we'll open it up. And we'll close some of these old files there. Great. So we're sitting at the start of the trace. And I'm going to start off by making an assumption that Jordy probably stopped recording after he saw the message box come up. So I'm just going to push the go button and go to the end of the trace. Okay. And so we look down at the stack and we see that the message box is still on the stack there. So our theory was right. And again, this emphasizes the fact that when you have your repro captured and there's really no cost to going past where you want to execute, you can just test theories, and if they don't work out, you try something else. So in this case, the theory was right. So let's take a look at what this code is doing when it calls message box. So we'll scroll up a little bit. And so this is fairly typical code. It calls getLastError to find out what the error code was. It formats it using format message, and then it displays it using message box. Now, the fact that it said operation completed successfully, that likely means the error code was 0. We can prove that by using a standard WinDBG command, GLE for getLastError. Yep, there it is, operation completed successfully. Okay, so let's see how queries can help us find this problem. So the first thing, so our basic idea is that in Win32, a common pattern is when APIs fail, they return false. And if you want more information, you have to call getLastError to get the information, a more detailed error code. Now, if you forget to call getLastError soon enough and you call some other Win32 API, it usually the error code gets set back to 0 and you end up with lovely message boxes like that. So what we're looking for is an error code that was returned that was non-zero before message box was called. So let's use queries and see what that looks like. So for now, I'm going to slide this over so we have plenty of room, and I'm going to clear the console window. So we access queries through the debugger data model that we talked about earlier, through the dx command. And what we're going to do is we're going to capture all of the calls to getLastError and to message box. And I'm going to assign it to a variable so that we can do some other things to it after it's ready. So we're going to go to the current session and use the tab key to have IntelliSense help us find some of this. And I know kernel base has getLastError. And user32 has message box W on the stack. We hit enter, and it runs for a few seconds, and it returns some results. Okay, so that doesn't look like very interesting results. So let's just clear the screen and display it as a table. And to do that, we use -G for the grid command. And I'm going to use my previous variable. And we can see this time that the results came up much quicker. So it caches query results in memory as you execute them to save time. Okay, so here's our table of information. And one of the things I notice is look at all these zeros. A lot of the times there's no error, but code is continually calling get last error, getting a 0. And so that's a lot of noise. We'd like to get that out of the way. So let's filter out the zeros. So I'm going to clear the screen again and use the up arrow key to bring up a previous query, and we'll add to this. And so here we're going to use a link query. And this is link with a Q, not a K. This is not the linker. And link is a query technology that's common in C#, and we have more information about it on our blog if you haven't seen it before. But what we're going to do is use the tab key. We're going to do a where clause, and we're going to limit what we see. The where clause takes a lambda, so I'm just going to use X to represent one particular call and say, okay, I want to keep anything where the function name contains a message box, because I noticed that message box returns 0. We don't want to filter that out. Or the return value is not equal to 0. Okay, so we'll do that. Okay, now when we scroll up, we don't see any 0 error codes. That's nice. We actually filtered out about 90% of the calls in this particular trace file. So now the other going back to what our goal was to find an error code that was set before message box was called. And so what we need to do is sort these things by the time that they occurred in. Okay, so I'm going to clear the screen, up arrow again, so we can just refine things over time here. And I'm going to use an order by, which is another link method that also takes a lambda. And the lambda tells us which field we want to sort on. So I'm going to sort on the time start field. Okay, and I also noticed that down here, if you get, it shows 100 results by default, and we see that there's some ellipses here. And so I'm going to make one more refinement to this, which is I'm going to add a comma on the end, and I'm just going to say, give me like 1,000 results. Okay, so now I have all of my results, and now let's see if we can find the message box. Okay, so I found the message box call, and we see that before that, the first non-zero error code was a 2. That's an interesting error code. Let's go time travel there and take a look at what we got. So we click on that, and it shows us the time travel thing here. And where is my scroll? Oh, there it is. Thank you, scroll bar. Okay, and we click on time travel, and it takes us to the time travel position. And we see our error completed successfully. And let's go down. Let's see here. Click on the right one. I think I missed the right one here. Clicking can be challenging at times. Scroll up to message box. Okay, and we go to on file open. And our file name is 0 there. That's not good. Oh, I forgot the time. Thank you. Thank you. Okay. All right, this looks better. So we do get last error, and there's our system cannot find the file specified. You see we're calling into the media player. Let's go to open file. And we see that the file name was passed in was CppCon demo.txt. That's not a very good media player option there, Jordy. Okay, so problem solved.
Okay, going back to the slides, what we have learned is in addition, I don't know how to open files. Send me a trace, not a repro, as we said before, that's something that works very well. The power of queries, and then a little bit of C# at CppCon, link. So, what's next? What are we planning for the future? Improve our recording experience. We talked, there is some overhead. We have done work from the days that research set out to prove that this was doable to shipping on the performance of the replay side on a couple of orders of magnitude improvement. And the reason is people record for 5 minutes and they replay for 4 or 5 hours. So cutting an hour out of those 4 was a bigger win than cutting a minute out of 5. Very powerful query support. We want to invest that in data space heavily. We want to do dynamic code analysis. We have a trace that explains us everything that happens, so we want to use it to find leaks or to find freeze, double freeze or use after free or this kind of stuff. And then we want to add kernel level tracing support to this tool, so you can do this on a driver that you are developing for Windows or whatever it happens to be. If you want to know how we are going to do some of these things, there is a clue at the bottom right-hand side corner of the slide. And with that, I'm going to move to questions that I didn't save. Oh. Do you remember the questions?
Jordy? Yeah, you forgot to save them again, didn't you?
Yes.
Yeah. Well, this happened a fair amount while we were practicing, so I didn't tell you this, but I secretly recorded the Notepad session when you were typing the questions in, so that we have a hope of getting them back. So may I?
Please.
Okay. Okay. All right, I hope this works. Let's see here. Okay, Alt-Tab. Okay, so we'll stop debugging here. And we'll open trace file from documents. Sorry. Down here in documents, TTD traces. Here we are. So before I open this, I just wanted to point out briefly, you can see that when we launched Notepad, you might have noticed it took a little while to launch, but the typing speed was pretty interactive, and it produced a file that's roughly 200 megabytes. That's not so bad. It probably contains about on the order of 200 million instructions, something like that. So let's open the file. And so what I did is I made a little JavaScript file that's going to try to dig out these things. So go down to here, and we'll open up our JavaScript. Great. And let's give ourselves some room to see the code here. So this is a feature of WinDBG, that you can actually write JavaScript and do imperative things like executing instructions immediately, or you can actually extend the data model that we've been talking about. So invoke script is like main in C++, and debug logs just like printf. So the basic idea is Notepad uses a window edit control, and the edit control holds a piece of locally allocated memory. And so if Notepad wanted to load or save text from what you're typing, it would have to be able to get at that memory. And in Windows, the way you get at that memory is through a message. So I'll briefly show you, I have some code that finds the text handle, that it remembers what position it's at so it can restore to that point when it's done, and it finds the text locations where the text was updated, and then does some simple things like appending to a vector, finding the unique strings, and prints them out. And in particular, I wanted to show you that you can do queries inside of JavaScript as well, and it looks very similar to DX. Here we start with the host's current session, and we go to TTD calls, look for send message, and the edit handle message, which is parameter 1 of send message, and then we do another query to find the memory, and hopefully, if we're all got it right, we bring that over, and it says, here are the unique lines from the Notepad session. This looks like the questions we asked at the beginning. So there you go, Jordy.
Thank you. So before answering the questions, let's go back to the slides for a moment. And let's see what we learn on this. Ken saves the day again. The debugger is scriptable, and now we did C# at the CppCon, and now we're doing JavaScript at the CppCon. So apparently C++ is not the only language we can use. Now, going back to the questions, how does this differ from RR? Single core versus multi-core, different characteristics on the performance overhead during record. Depends on the type of program and the number of cores you have on your machine. One will be better than the other on the overhead that you see. But the basic principles are the same on how this works. Is this Windows only, or which version of Windows? Actually, this is on the WinDBG preview, so you actually have to have an up-to-date version of Windows 10. This will be available on the kits, then some of the restrictions will be lifted, but right now it's an up-to-date version of Windows 10. Okay, and with that, now for real, let's open the floor for questions. And no.
I don't think you ever said how to record trace, unless I missed it.
Let me show, and what I'm going to do is use this moment to also show a case where our overhead is significant, so that you guys see that sometimes in Notepad you saw us type, and that came as fine, or even on the debugger you saw us use this. So if I'm going to use actually, let me launch a Notepad this way. No, sorry. From here, launch executable, click this checkbox, record process with time travel debugging, and that will launch, in this case, the debugger. If I do something as uninteresting as this and click on the record, it should launch Notepad. And now typing works normally. However, if I want to show the open file dialog, this will take a while. And the reason is this dialog does a ton of work. This dialog launches 14 threads, calculates icons and thumbnails. It actually, it's still usable, but there is some overhead sometimes. And as we said, that's.
So is there, does this require any compiler or linker support?
None. This will record, in fact, it's one of the conditions we had, since we support code that sometimes we haven't written at Microsoft, we don't have symbols for it, or we don't have anything. This works just fine.
Yeah, so that's just the normal Notepad that's installed with Windows. It's no special modifications.
No special modification. The only thing we did is we created a start menu shortcut to launch it under the recorder, but that was it.
So you don't even need symbols to do the
No.
record? I mean, to do the playback, I guess you do.
No, you need symbols if you want to debug with symbols, but I have debugged without symbols just fine with this. And this is a normal machine with public symbols of Microsoft, so we have the public symbols of Notepad. Sorry, there was a question on the back in the middle.
Oh, yeah, actually, if people could go to the microphones, that would be easiest, because then we don't have to keep repeating questions.
In fact, if you don't mind, I'm going to change my glasses so I see you.
What size of files are the traces? Like, how much resources does that take?
So the size of the trace varies by the number of instructions you execute. The more instructions you execute, the better. What we do is when we start recording, we take a dump of the entire process. So that is a participant, and then on a steady record, we do a bit per instruction. Okay, but it will vary. The open file dialog is actually disastrous for us. But there are other places where we can do much less than that. But that's approximately the case. The overhead is mainly record is some overhead. Replay, some cases will be faster than live debugging, some cases not. And the overhead of the recorder is memory intensive right now. We have work on the record side, as we said, to improve that significantly. Thank you. Thank you.
Over here. You mentioned that you obviously can't modify memory on the replay. Can you still execute code? So can I call a function that doesn't modify memory?
No.
That was a fast answer.
I have actually two questions. One of them, can I attach the recorder while the process is executing?
So a few notes. You can attach to anything that you can debug, pretty much. There are a couple of corner cases, but in general, if you can debug it, you can attach to it or you can launch it. You can attach to UWA processes. You cannot not launch them under the traces just yet. The other thing to note is when you stop, we terminate the process. Okay, that's relevant. We have a couple of work items to remove that, but that's.
Thank you. And in general, I also had a question. What are the limitations so that we know what to not expect?
If you cannot debug the process, we have actually done work to avoid us recording things that you cannot debug. That means sometimes if you have antivirus software on your machine that blocks process write across, we will not work. You have to disable the antivirus software. If that makes any sense.
Cool.
Yeah, I'd also like to add, if you're using public symbols with queries right now, it doesn't resolve the names. It'll just say unknown symbols. So that's another thing we need to fix. If you know your own code where you have full PDB information, it's no problem. But like pulling out kernel base's name there today requires private symbols, but we'll fix that soon.
Awesome. Thank you.
You showed the time travel debugging on a large-scale application. I want to know what the impact is when you're running on a huge scale application. Like in my case, it's a server application that sometimes runs for 10 minutes or an hour before it has problems and takes 10 to 20 gigabytes of memory. What is the most efficient way to work with it, and how? What's about size, performance?
That will be a long question to answer. We will be at the table outside to answer it. I have recorded this for hours, but the traces come back really, 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 really big. Just to set expectations. We use it, for honest, on a change servers, which are 64 gigs of RAM, fully packed, and it works, but the overhead is measurable. You will see it with the naked eye, the overhead, just to set expectations. Since we still have time, but if not, if you see people with these shirts, you can ask them questions as well. And just putting up here the other Microsoft talks so that you guys know where they are, please.
I have two questions. First of them, is it possible to record only 2 seconds of application last time when the application working before crash?
You need to know how to start recording, but for example, if you touch the debugger and you have a particular event, and in the debugger, then you do work to suspend the process and attach. There are things to do there. It's an area where we will be making things easier for you.
I show the situation. I start test and test agents and under debugging, and when test crash, sometimes I need the last seconds to understand what happened.
You still need to start a recorder yourself.
Yeah.
But you're gonna start since you can attach, you're gonna start the recorder when you see fit.
And second question was about administrative rights. Is it possible to not use administrative rights because test agents must be clean?
Not at this moment in time. We have been talking inside of Microsoft on how to remove that requirement, but right now we rely on a couple of APIs that require admin rights. We are working through that.
Okay, thanks.
Hi there. Are there any plans to integrate that into Visual Studio?
So we are working with the Visual Studio team, and they are analyzing the product and how it would integrate. If you would like to give them feedback, email ttdvs@microsoft.com and give them your thoughts, and they will be happy to hear about that. And to be clear, they expect someone to email them if you want to do that. So please do.
So I'm on Visual Studio. If you want to see this happen and you send a mail, that increases the chance of it happening.
Sorry, for those.
I was going to say, people want this. It's a lot more leverage than just an idea coming from the likes of the DBG team.
So, for those that did not hear the person without the microphone, if you send an email, it will really increase the chances of this happening. So please do if you want to see this happen.
Thank you, Andrew.
Hello.
Okay.
What's
We're out of time. I'm happy to answer questions, but just to be clear, we're out of time.